Welcome to qnawire.
Okay, so for this problem, you have two masses that are attached with a rod or string, and there's force in the middle that's pulling this thing. And then after a certain amount of time, the two masses collide, and they're still being pulled by this constant force here. So between here and here, this force has applied some energy system that has made it move the way it did. So you're given that this is distance d, the distance between the point of application of the force. And then you are also given that these masses are m, and you're told that these stick together and in a perfectly inelastic collision. So the first thing that you want to, so here they tell you that this thing now is moving over here with velocity v. So this is time equal to 0, and this is time equal to t here. So essentially, you have some increase in energy as this force is being applied. So the first thing that they want you to calculate is the velocity in terms of the quantities that you're given. So in terms of F, D, L, and the mass. So the one thing that you want to take note of is that when this thing moves through, the center of mass has actually moved a slightly lower distance. So that's the distance that moved by the center of mass. So assuming that these things collapse on themselves, what you notice is that this distance here is actually equal to the big distance here minus half the length of this rod here, because this would essentially now be, so this would be now L over 2. So essentially, D in this case is the distance that the center of mass moves plus L over 2. Or you can write it as D center of mass is equal to D minus L over 2. And this is important because essentially what we want to do now is we want to estimate that by calculating the average velocity that this thing has through this motion. So you know that the average velocity, so V average, is just V initial plus V final over 2 in this case, because you have the initial velocity, final velocity, and you just want the average of these two velocities. So you'll notice since V initial is 0, that's just V final over 2, and V final is just V. So the final velocity is just V over 2, or the average velocity is V over 2. So you have an average velocity and you have a distance traveled by the center of mass. So if you want, now we can calculate the time that it takes to do this motion that the object does. So notice that time is just going to be the distance over the speed that it's traveling at. So this is going to be D minus L over 2 divided by V over 2 in this case. And when you simplify this, you'll know that you come up with an expression for delta t. But in this case, let's just leave it as it is here. So now that you have your delta t, you can go on to now write your momentum equation. So you know that this force is acting through this time delta t here, and you don't know what size the force is, but you want to express all of this in terms of the quantities that you're given. So you're not given this delta t here, so that's what you want to find. So we know that the impulse F delta t is always going to be equal to some change in momentum. And we know that since this thing was not moving at the beginning, but it was now moving with velocity v, and these things are stuck together. So this is twice the mass times the velocity. So the change in momentum is actually 2mv. So now to find the force, I'm just going to divide the change in momentum by delta t. And we know that delta t is given by this expression. And so now what we do is we just say 2mv over delta t, in this case is d minus L over 2 over v2, like so. So now we know, now we can express the velocity in terms of f, and we don't have a delta t anymore. So notice that if you simplify this, you will have an expression that looks like, so it should read 2mv squared over d minus L over 2d minus L, essentially, once you simplify it. So this is equal to f. So now to find the velocity, you just need to move these variables to the other side and then take the square root. So this is going to be the square root of 2d minus L over the numerator here, which is 2m. But remember, you have moved it to this side, so this is also has f in here because you're multiplying. So it's like cross multiplying this on the other side and taking the square root at the end. So this would be an expression for your velocity. So the next question is asking you to calculate how much energy this thing puts into the system, and how much of it is converted into internal energy of the system. So essentially, we want to use our work energy theorem to figure out what amount of energy besides kinetic energy the system has at that point. So we know that the work is always going to be equal to, so this is the work energy theorem, that the work is always going to be equal to change in kinetic energy, change in potential energy, a change in any other form of energy that is negligible for this problem here, plus a change in some internal energy. And we want to essentially calculate this expression here. So the change in potential, that's zero because these parts are on a flat surface. So the work energy theorem says the work we're doing with the system is going to go into kinetic energy plus some internal energy of the system. So now we know the change in kinetic energy, or we can calculate the change in kinetic energy, and we know what this force, we know how to calculate this work here because we know the force and we know the distance that it moved. So we can now explain this by saying the force times the distance, which is work done by a force, is always equal to the change in kinetic energy here is going to be half, but this is the combined mass because this is the final kinetic energy, v squared minus the initial kinetic energy at t is equal to 0, which is 0. This is plus some change in internal energy of the system. And notice that that cancels there. So Fd is equal to essentially mv, that's mv squared minus 0 plus delta E internal. So now we can go ahead and simplify this further. So we know that Fd minus mv squared minus mv squared is going to be equal to the change in internal energy. So now we can go ahead and plug in all the things that we are actually given in the problem. So we want to express this V here in terms of the force that we have. And this, so now we can just say FD minus M. And then for V squared, we just plug in what we had for V squared. So V squared, notice it's just 2D minus L multiplied by F all over 2M, like that. So this is M, this is M, so that cancels here. So notice that you have, so now this is going to be 2dF over 2. So this is now FD minus 2FD over 2. Notice that you have 2 here. And then minus FL over 2. This is equal to the change in internal energy of the system. So notice if you subtract this, so now we're just simplifying. So this becomes FD over, so this, notice this FD over 2, so that goes away. And hence this also goes away because that says FD minus FD. And then, so there was a negative sign here, which makes that a positive sign over here. So that expression ends up being half FL is the change in internal energy of the system.